turn right, put the indicator on, and of course this thing flashes periodically. It's most likely built on an RC circuit, but I could build it on an RL circuit, which isn't quite as straightforward. And if I wanted to do that, then I could do the same thing. So I could tune the time scale to match whatever frequency of flashing I want to have happen. So there are, I think, not at least coming to mind, fewer immediate examples of how it's going to be used in this sort of tuning sense, but I'm sure there are plenty of others you guys will think of if some of you are going on to be electrical engineers. All right, so let's see. Energy stored. Yeah, let's talk about that, and then I'm going to make a couple of comments about things that use inductors and inductances in daily life. So let's come on to this energy stored question. Okay. So, still up there? Yep. So, loop rule result, which is at the top of the right-hand board up here, tells us the following. I'm going to take this and multiply everything by I. Okay, so it may seem a little strange, but I'm going to multiply the entire equation by the current. And this tells me that epsilon I equals Li di by dt plus I squared R. Okay, so there are some terms in here that should look kind of familiar. This is the power dissipated most likely in the form of heat. Thermal dissipation in the resistor. This is just E dq by dt, which is the rate at which the battery does work. So this then should be, the way to think about this, is the rate at which energy is stored in the inductor. Okay, so all I've done is multiply by I here to get things in terms of power units. We know what this is. Energy provided by the EMF source. This is thermal dissipation in the resistor. So again, this is the rate at which energy is stored. Power in a sense, but we're actually storing the energy here. So this is the rate at which energy is being stored in the inductor. And so, again, a slightly maybe unfamiliar way of looking at this, but it's unit-wise correct. Now I'm going to extrapolate the conservative force. The magnetic force is conservative, the same way the electric Coulomb force is conservative. Therefore, it has an associated potential energy. Now we're going to call it U with a subscript L, because this is specifically for potential energy stored in the magnetic field of an inductor. It's this, and so I can basically integrate this to get an expression for U as a function of current. So let me just do that, and again, I'm not going to have you worry about doing any of this on an exam or on a homework. It's only the end result that I care about. I'm going to separate terms here. I'm going to integrate from some initial current to some final current. And I don't like to go fast in cases like this because it tends to possibly lose you along the way, but again, it's the end result that matters. turns out that I can write the energy stored by this analysis as just being 1/2 times the inductance times the square of the current. Okay? So we got to this from a slightly unfamiliar route, but if you follow each step, it makes sense. I'm looking basically at energy and power balance in my circuit, and then I'm taking this as being the rate at which I store energy in the inductor, separate variables, integrate, and this gives me the energy stored in the magnetic field. Okay? So energy stored in the magnetic field. All right. Anyone recall the analogous result we had a month ago for the energy stored in the electric field of a capacitor? Yes.
1/2 CV squared.
Okay. Or 1/2 Q squared over C, or the other third permutation, depending on which 2 of the 3 variables you have. Good. Okay. So beautiful analogies here, and that kind of, I think, is all I want to say about RL circuits. I'll give you at least 1 or 2 problems on the next homework on this, but I'm not going to pursue it too much. Delphine?
If you have can you also add them like capacitors? Like, does that relationship hold, or are we always just going to be dealing with one inductor at a time?
Okay. So you can see I'm pushing this less than I did with capacitors, and so good question. I'm not going to have you worry about multiple inductors in these circuits. Okay. So you only have to worry about simple RL circuits, not multiple inductor circuits. Good. Thank you for asking that. Okay. At this point, I have just a few minutes left. Which means I'm going to run out of time in terms of saying something quantitative about mutual inductance. All right, let me just ask you for some thoughts about where do you see inductors or inductive effects in daily life? Things that you've experienced in some cases already today. Where have you seen inductors at work? Or inductive effects? Have you seen something to do with magnets and magnetic fluxes? Maybe circuits carrying changing currents. Any thoughts? Yes, sir. Okay, thank you, Louise. Okay, inductive cooking, yeah. Okay, we've already talked about that on Tuesday. Anything else? Yeah.
Electricity generation?
Sure. Okay, yep. Based on this, slightly less obvious than things we haven't already talked about. Yes?
Wireless charging.
Okay. Wireless phone charging. Okay, whatever you put those pads things on, is your wireless phone. So I'm trying to separate this so it's clearly not connected. Okay, I gotta go closer. Sure. That will be one good example of inductive effects. Anything else?
Raising microwaves.
In what sense?
The field changes to the atoms and the different atoms.
Say that one more time.
The fields, the magnetic field changes so that the atoms water.
Okay. Interesting comment. Yeah, I'm going to keep that in mind until next week, because what you're really doing there is relying more directly on the combination of, in fact, changing magnetic and electric fields, aka electromagnetic waves. So that's some relevance, yeah. Transformer, okay, that was going to be one of the things I was going to talk about and show you a little bit. I'm still going to show you, but I won't have time to do it quantitatively. Okay, a few other things that you may have experienced inductive effects on. All of you, I have no doubt, are carrying around with you either, I don't know, MTA Metro cards or credit cards or debit cards. How do they work? Yes, without reading off your cell phone, okay?
To be fair, she had it up before you said it.
I know, but now you've absorbed the information, so.
That has tiny little things that can be magnetized to produce a strong magnetic.
Okay, just says they have tiny little magnetic things that can be magnetized to produce magnetic fields. Yes, no.
So the magnetic strip on the back of it is alternating magnets.
Yep. Yep.
And they encode like zeros and ones, and as you swipe them through your credit card or like a card that we're talking about, it induces a magnetic field, which is encoding the data from the magnets.
Yep. Okay, nice. So here's my CUID card. This is not going to work, by the way. It would be amazing if it did. Magnetic strip on the back is encoded in exactly the way Noah just described. It's got little domains, briefly a little bit about domains, where all of the magnetic moments are aligned in a certain direction. If I send this past a coil like this, as it moves, it's changing the magnetic field and the magnetic flux that's passing through this coil. Okay? The reason you have to swipe these things is there needs to be relative motion so that the flux changes. Just stick it there, nothing's changing. So you're not inducing anything. But by doing this, I'm inducing an EMF and a current way too small to be observed in this case. If you hook it up to some current detector and then you basically encode that and send it off to some database to match it with a defined series of zeros and ones that match your particular unique identifier, that's a way of confirming it's you, that you're the specific card holder, and then of course the transaction takes place. So swipe card readers are very much based on inductive effects. Okay? So that's good. One other quick thing that I'm going to show you a quick example of mutual inductance and transformers, and then we're going to stop. Don't get too antsy just yet. Those of you who drive vehicles, most of you, and you're driving along places that have stoplights, but stoplights that are triggered by vehicles being at the traffic light. How do they work?
So, right weekend, the line, you language about and it says we drive a little car over it, and it says the change in
Okay. Yeah, roughly speaking, the stoplight, the road near the stoplight has basically a large conductive coil buried in the road surface, and that has an inductance associated with it. If you drive your car across it, your car being a conductor to a large extent, it will change the inductance, and the circuits are set up in a way that you can actually detect that and use that to trigger the light changes. Okay, so bear with me, a couple last things. Mutual inductance, we've already talked about this in the case of this solenoid and this solenoid. If you think about it now, I can tune the effect from here to here by changing the relative number of coils from this one to this one. And it induces an EMF, and so I can use this as a way of transforming, which is to say changing the voltage of one power supply source compared to another. Okay? So just to show you this, and then we'll stop, but before you guys pack up and go, I want you to read a page and a half of my notes and probably a comparable amount of material in the textbook on mutual inductance. Very simple analysis based on stuff we've already covered. And I would like to look at it. Let me just show you how a transformer works. And again, a transformer is a device that takes intrinsically alternating current. Therefore, it's changing. We have inductive effects built into it. It takes intrinsically alternating current, drives it through one solenoid, connects one solenoid to another by some magnetic flux linkage, and allows us to tune what voltage change we get out of this. Now, I can either increase the voltage by having a larger number of coils in the secondary pickup coil compared to the first one, or I can decrease the voltage by flipping the ratio. You have fewer coils in the second compared to the first. So this gives rise to what's called step-up, step-down transformers, depending on the relative number of coils. What you're seeing here are two traces from an oscilloscope. You have some idea now of how an oscilloscope works, lots of electromagnetism in it. The blue one, I believe, is the current, alternating current, that's being provided by an external power supply here. The interesting part of all of this is what's at the front here. You see now that this is one solenoid on the left. There's a second solenoid. They're no longer coaxial like we saw with the light in that solenoid. They're now in a loop. And the loop is in the sense channeled by having steel all the way around it, which is this blue square. So I want to show you two quick things and then I'm going to let you go. So this is energized now, so there's alternating current passing through this. It's got an iron core. The iron core is part of a square which channels the magnetic field lines around, channels them through this second one, and then the whitish trace on there is the pickup current that comes out of the second coil, and you see that they are both in phase and they are about the same amplitude. Okay? So this is telling me that I have essentially picked up all of the magnetic flux from here into here, and I've induced an EMF that's of comparable magnitude. I'm going to break this magnetic flux loop by taking away part of the steel. Now there's way less linkage in terms of flux between this one and this one. There's still some, mostly provided by this thing down here, but way less. So it makes it a much less effective transformer. Let me put it back. Now what I'm going to show you is a way to step up or step down. So at present I've got equal number of coils here, equal number of coils here. I'm going to make a connection change. I can connect this so that I only pick up the current through half of these coils, and I'm about to do that now. So watch what happens. I'm going to halve the number of coils in my pickup coil. This is the right one. Whoops, double it. Okay. Interesting. I guess my assistant Ken set it up so that in fact it was already on twice the number. Okay. Confusing. All right. So it's now on twice the number of coils in the pickup, and here it's on the same number of coils. And you see I was able to step up the voltage by simply changing the number of coils in my transformer. And I can do the same thing on this side, though at this point I'm unsure which way to set it up. Let's see what happens. Okay, not obvious. All right. Take a look at my notes on this. Take a look at a page and a half in the textbook. Have a good one again.